Swayam Prabha. Digital India. Educated India.
Certain theories which explain stability and reactivity of an cycloalkanes. So in this session we will be looking towards one of an theory. So learner will be able to understand bare strength theory, which is used to understand stability and reactivity of cycloalkanes with its limitation. After that, learner will be able to understand Coulson-Moffat's model, which is used to understand bend bond in cycloalkanes, and it is also called modification of bare strength theory. Now we'll see the contents of this session. Firstly, introduction to cycloalkanes. So what actually cycloalkanes are and how they are different from an alkanes. So we will be looking in it. After that, nomenclature, so naming of that cycloalkanes, and there are certain symbols that are being utilized for denotion of an cycloalkanes. So one of an theory that is explaining the stability and reactivity of an cycloalkanes, why certain compounds are reactive than another. So we will be looking that theory, that is bare strength theory with its limitation. After that, we will be looking Coulson and Moffat's modification. So it is also said to be a modification, or it is also said to be a model, or this theory it is also called banana theory. because it is having some structural similarities with banana. So it is also called banana theory, and it is modification of a bare strain theory. So it has explained why, uh, how the angle, what the angles are being explained by bare strain theory. So this model, so it shows some little bit modification, how actually angles are and why they can sustain the structure. So firstly, we will be looking introduction to cycloalkanes. Cycloalkanes, or they are also called cycloparaffins, are saturated hydrocarbons in which the carbon atoms are joined by a single covalent bond to form a ring. So whatever we are seeing here, it is only an cycloalkane part. So cycloalkenes, they contains an pi bonds, but cycloalkenes, it contains only single covalent bond to form a ring. So there will be no involvement of a double bond, and that is why it is said saturated hydrocarbon. They are also called alicyclic compounds. So in case of organic chemistry 1, you might have studied about classification of an organic compounds. So in that you may have come across alicyclic compounds. The unsubstituted cycloalkanes form homologous series with general formula CnH2n. The first member of the series is cyclopropane. So there cannot be a small molecule than cyclopropane, because with ethane we cannot join both the bonds or it will become an ethene, right? So to cyclopropane, it is the first member, and series continues. And you can see in the structure of an cyclopropane, now whatever we have said over here, that is a single covalent bond. See this single covalent bond, it is joined with it joins two carbon, and these are saturated hydrocarbons. So there is only hydrogen and carbon with saturated form, and there is no unsaturated, because we are dealing with now cycloalkanes, and as cycloalkanes, they are always saturated and having a formula CnH2n. So number of uh, carbon multiplied with the number of hydrogen into 2. So here also we can see that number of carbon are 3, and H into 2n means 3 into 2, it becomes 6. So same will be the formula. So this one is in general formula for cycloalkanes. Now we'll see the nomenclature of this cycloalkanes. So name of an unsubstituted cycloalkane is obtained by attaching the prefix cyclo to the name of corresponding normal alkene having the same number of carbon atom as in the ring. So the meaning of the first sentence is that if a structure it is of an propane, just we are attaching cyclo. So that cyclo prefix, it is used in the nomenclature. So this compound, it will become an cyclopropane. So whatever the numbers of carbon we see in the alkane, so same number of carbon they should be in the ring, and when it resembles same, then we are using, when it is a ring system, then we are using alkane with an cyclo as an prefix. The substituent on the ring are named and their positions are indicated by the number. The ring is numbered so that carbon bearing the substituent will have the lowest number. So whatever the substituents are been present, so they can be indicated by the numbers. If substituents are more than one, so there is need of an indicating number. If substituent is just only one, so there is no need of an indicating the number. So we will see the example, and the numbering should be in the such a way that the carbon the substituent should have an lowest number with the carbon corresponding. See this structure, it is of an methyl cyclopentane. So this ring it is and cyclopentane ring. So we will also see what is actually symbols they are being utilized to uh, denote cycloalkanes. So this symbol it is utilized to denote an cyclopentane ring, and it is having a substitution methyl. So that is why it is said to methyl cyclopentane. And now here there is no need of a number because a substituent is only one, so it can be at any position, so there is no matter. And if substituents are more than one, then we need to number, and numbering should be in the lowest substituent carbon bearing. Now here we can see a structure of an cyclohexane, and this cyclohexane it has been substituted by two substituent. So first one is chloro and second one is an methyl. So a question might be coming in your mind that why it has not been started numbering from a methyl group. So you might be knowing that whenever we are coming with an nomenclature, so there are some priorities for certain substituents. So chlorine or halogens are having more priority compared to this alkyl, right? And that is why the numbering starts from an chlorine. So chlorine will have a number 1, after that second carbon and third carbon. So the last line here it is indicated that ring number, so the numbering of the ring, the carbon bearing substituent will have the lowest number. So we cannot number by this way, that first number, second number, third number, fourth number and fifth, right? So we should identify the lowest numbering of an carbon. So it will start from this side only, not by this side. So the name of a compound, it is 1-chloro-3-methyl cyclohexane. Stability of first few cycloalkanes. So first few cycloalkanes, it is quite important because it has failed for higher cycloalkanes like cyclohexane, cyclooctane, cycloheptane. So it is represented. It has been explaining stability only of few first cycloalkanes. Few first cycloalkanes means cyclopropane, cyclobutane, and cyclopentane. So Bayer theory is based on the fact that a normal angle between any pair of bond of carbon, it is 109 degree and 28 minute. So this thing, it you might have studied in case of an sp3 hybridization. Here it is covalent bond. That is why we will deal only with sp3 hybridization, because cycloalkane contains an covalent bond. So in normal alkane, it has been studied, or you may have studied about an this bond angle between carbon and carbon and hydrogens. So this bond angle, it is almost 109 degree and 28 minute. The Bayer postulated that any deviation of an bond angle from a normal tetrahedral value would impose a condition of internal strain on the ring. So the normal value, it is 109 degree 28 minute, and any deviation in the bond angle from the normal tetrahedral value causes the strain. So that strain, it is internal on the ring. And as the molecule, like it starts from an cyclopropane, it starts with a small molecule like an cyclopropane, first member of an cycloalkanes. So internal strain in case of an cyclopropane, it is quite higher compared to an other cycloalkanes. So it increases with number of an carbon, but up to a certain limit only Bayer theory can be applied, not for an higher cycloalkanes. So we will see one by one. And this deviation, it is related with an stability of that molecule. So higher will be the deviation, higher will be the instability in that molecule. So he assumed that all the cycloalkanes were planar. Obviously they are planar because they are been sp2 hybridized, so they belong in all in one plane, and thus calculated the angle through which each of the valency bond was deflected from the normal direction in the formation of various ring. When it forms a ring, so the normal angle between whatever the normal angle it is as per the hybridization, that is 109 degree 28 minute. So that cannot be seen in case of an valence bond of an each carbon. So it deviates. So it deviates by a certain angle, and that certain angle, it causes instability, and this instability is nothing but an strain. So it is an internal strain between carbon and carbon, and due to this change in bond angle, reactivity of the molecule also changes, or the stability of that angle also changes. This is called angle strain, which determine the stability of the ring. Now we will be looking one by one example. So Bayer strain theory for cyclopropane. In cyclopropane, 3 carbon atoms occupy the corner of an equilateral triangle. So equilateral triangle because all the sides are equal for the triangle. Thus the cyclopropane has carbon bond angle of an 60 degree. This implies that normal tetrahedral angle of 109 degree 28 minute between any two bond is compressed to 60 degree. So and that each of the bond involved is pulled by almost 24 degree and 44 minute. So this is the formula that how we can calculate the strain. So actual angle, it is 60 degree, but by theory it should be 109 degree and 28 minutes. So half it is because we are calculating for both the sides, so that is why it is written half. So by structure it can be understood easily. So this is the structure of an cyclopropane. So these are the three bonds, covalent bonds, and the actual angle, it should be 109 degree and 28 minutes. So all the tetrahedral structures, they do have this 109 degree and 28 minute angle, but it is only an imaginary. The actual angle, it is 60 degree. So the angle in the reality, it is 60 degree, and that is why now the remaining space in between these two, means imaginary and actual angle, it is almost 24 degree and 44 minute. So this angle, it is said to be an angle strain. So totally it becomes 48 degree. So 48 degree, but by the both sides, and that is why it has been divided by half. So we can calculate for each carbon. So collectively it becomes 48, and by dividing it by half it becomes 24 degree and 44 minute. So this angle, it is said to be an angle strain, and that is why it shows instability, because to maintain the stability of a structure, it should be 109 degree, but it is not, and it has been reduced and it has been compressed by 24 degree, and it has now become 60 degree. And as it becomes closer, so cyclopropane is the first member of this cycloalkane ring, and as it becomes closer, so closer it is in case of only cyclopropane. When it becomes square, or when it becomes pentagon, and when it becomes an higher cycloalkane, so angle or strain angle, it reduces. So the first member, that is cyclopropane, it has most angle, that is 24. So cyclobutane, as we have seen, it can be shown by a square. In cyclobutane, the 4 carbon atom occupy the corner of equilateral square. So as like equilateral triangle, all the sides are similar. So all the sides, they are similar. So it is why it is called equilateral square. Thus cyclobutane has 4 carbon-carbon bond and bond angle of 90 degree. This implies that the normal tetrahedral angle of 109 degree and 28 minutes between any two bond is compressed to 90 degree, and that each of the bond is involved by pull of 9 degree and 44 minutes. So from structure it can be understood. So this is the structure of an cyclobutane, and the actual angle between carbon-carbon, it is 90 degree. This bond angle, it is 90 degree. But it should be, as per the theory of a tetrahedral theory, it should be 109 degree and 28 minutes. But it has been reduced to 90 degree, and this 90 degree, it is nothing. 90 degree, it it forms a strain, and this strain it is up to 9 degree and 44 minute. So it can be calculated by dividing the value by half, and we get the value of 9 degree and 44 minute, which represent the angle strain or deviation through which a bond bends from a normal tetrahedral direction. So normal it is 109 degree and 28 minute. So as compared to an cyclopropane, now the bond angle or the strain has reduced, and strain it was 24 in case of an cyclopropane, but now in case of an cyclobutane it is only almost 9 degree and 44 minute. So it has been reduced. So it is indicating the stability of an compounds. As the angle strain reduces, the stability of an compound increases. So we will be looking why cyclopropane is more reactive than any other cycloalkanes or cyclobutane. So we will be looking at for that concept also. So from this it can be understood, as the number of carbon increases, the strain angle it also decreases and stability increases. Now we'll move towards the further structure, that is cyclopentane. In cyclopentane, the 5 carbon atoms occupy the corners of an pentagon. Thus the pentagon has 5 carbon with a bond angle of 108 degree. This implies that normal tetrahedral angle 109 degree and 28 minute between any two bond is compressed to 108, and that each of the bond is involved in the pull by just 44 minute, 0 degree and 44 minute. So it is almost half. Only the value it is half. So there is very less deviation in case of an cyclopentane compared to cyclopropane and cyclobutane. So cyclopropane highest, after that cyclobutane, and after that cyclopentane. So cyclopentane it is so as per the theory, the cyclohexane has a negative angle strain. So we will look how actually it is. In cyclohexane, the 6 carbon atom occupy the corners of an hexagon. Structure it is an hexagon. Thus, the hexagon has 6 carbon bond angle of an 120 degree. So normal tetrahedral angle it is 109 degree and 28 minute, and this hexagon has an 120 degree. This implies that the normal tetrahedral angle of an 109 degree and 28 minute between the two bond is compressed. Now it is not compressed actually, it is now opening, or it is outward to 120 degree, and that each of the bond involved is pulled by minus 5 degree and 16 minute. So if we look at the structure, here you can see the structure of an hexagon, that is cyclohexane. Each corner are having one carbon with and two hydrogens. So the normal angle, it should be 109 degree between the carbons, but in actual it is 120 degree. So it is beyond the normal, and beyond the normal means in normal it should be almost 109 degree, but in case it is 120, so it is having negative angle strain. So the stability, so as per this theory, the stability of an cyclohexane should be more, but not compared with an cyclopentane. In case of an cyclopentane, it is near to the normal, and as it is showing an negative strain, but cyclohexanes are quite stable than cyclopentanes, and also some higher cyclohexane also, they are quite stable. So this theory cannot explain in case of an cyclohexane what actually and how, what is the reason behind the stability. As it is a negative strain, it is not a positive strain, but it is strain, bond angle has widened, but this theory cannot explain in case of an cyclohexane. So it is limited only up to cyclopropane, cyclobutane and cyclopentane, but not for an cyclohexane. So we will see in the limitation also, and the value of minus 5 degree and 16 minute represent the angle strain, or the deviation through which each bond bends from normal tetrahedral direction. As per the Bayer strain theory, cyclopropane is more reactive than cyclobutane. Not as per the theory, but theory can be utilized to explain the reactivity of an cyclopropane. And cyclopropane is one of the most reactive species compared to another molecules of an cycloalkane family. And the reasons are very simple. The angle strain is maximum in case of an cyclopropane as compared to the cyclobutane or cyclopentane, or in case of an cyclohexane also. So according to this theory, cyclopropane should have highly strained molecule and consequently most unstable, because as we see the structure of an cyclopropane, it has been compressed to 60 degree, and compared to that, in case of an cyclobutane, it has compressed to 90 degree, and in case of an pentane, it has compressed to 108 degree. So cyclopropane is maximum having a maximum strain compared to other molecules of an cycloalkane family, and this results in stability of a molecule, and instability creates an reactivity. As molecule becomes stable, the reactivity decreases. The cyclopropane ring should therefore be expected to open up slightest provocation, and thus releasing the strain within it. Cyclopropane undergoes the ring opening reaction with bromine, hydrogen in presence of a nickel, after that HBr to give open chain addition product. Cyclopropane and almost cyclobutane also undergo a ring opening reaction, but reactivity of an cyclopropane is much faster compared to cyclobutane. And other higher molecules like cyclopentane or cyclohexane, they does not undergo the ring opening reaction. So that is due to the angle strain. So as the angle strain increases, the reactivity of a molecule increases and stability decreases. So cyclopropane is having a maximum reactivity due to maximum angle strain, and that is why it undergoes the ring opening reaction. Prediction: cyclohexane and higher members are found to be quite stable. So here there are some limitations of an bare strain theory, that as per the theory, as the number of an carbon increases, the strain should increases continuously. But it does not give, but it has failed to explain in case of an cyclohexanes. They do not undergo the ring opening reaction, instead they resemble open chain alkanes in reactivity, that is, they react by substitution. So we can also see some examples that cyclohexane ring undergo only substitution but not an ring opening. And which is explaining the structure of an cyclopropane, how actually it is. And it is modification. This theory is also called modification of a beer and strain, and it is also said to be a model, or it is also said to be a banana theory. And why it is so, we will be discussing. So this Coulson and Moffat's modification, so it is related with beer strain theory. This model is also known as concept of maximum overlap of carbon orbital, or bent bond, or banana bond theory. So it is also called bent bond theory or maximum overlap of an orbital. So that concept, it depends on maximum overlap of an carbon orbital, or also it is said to be an banana bond theory because the structure, it looks like an banana. The bent bond, see this bond, it is now a little bit different. So it is not an covalent bond, or it is not an pi bond. So it has shifted electron density, or the configuration has been changed due to this bent bond, and that is why it is said to be an bent bond theory. A bent bond is also known as an banana bond. This type of an covalent chemical bond with a geometry of somewhat indicative of an banana. See, in case of an covalent bond, the overlap, it is at the axis, but in case of an bent bond, overlap, it is not at the axis, or neither it is at the end. Means it is not directly a pi bond, or it is not an covalent bond. It is the bond in between these two, pi bond and covalent bond. When it becomes pi, it becomes cycloalkanes, and we are not studying cycloalkanes. We are studying here cycloalkanes. See the structure of an cyclopropane. If we look structure of an cyclopropane, so there are three covalent bond in between, and this covalent bond, these are arranged like these bananas, and that is why it is said to be an banana bond theory or bent bond theory. So these are nothing but bent bonds. So bent means what, they are not in the straight line, so they have been bent at the corners, and that is why it is said to be an banana bond theory. And if we look at the structure, so the overlap between carbon and carbon, so this overlap, it is not on the line. So this, it has shifted towards a new electron density. So electron density has been shifted, and that is why there is less maximum overlap, and due to this less maximum overlap, it becomes weaker and it is easy to break. The term itself is a general representation of an electron density or configuration resembling a similar band structure within a small ring molecule such as cyclopropane. So here we have taken the example of an cyclopropane, and configuration means three-dimensional structure of that molecule, how the actual arrangement is, and representation of an electron density, because we can see in the further slide how the electron density is it has been shifted from a normal. The sigma bond involves end on overlap, and pi bond involves side long overlap. Bend bond is intermediate between sigma and pi. See, axial overlap and lateral overlap, as we know it about sigma bond and pi bond. So sigma, when two orbitals they overlap at the axis, it is said to be an sigma. When overlap, it is at the lateral end, so they are said to be an pi bond. The bend bond, it is intermediate between this sigma and pi. So it is not at the end, or it is not side long. So it is in between. The overlap of being neither end or nor long side, this makes the overlap less efficient than sigma overlap, and the cyclopropane carbon-carbon bond weaker than the normal carbon-carbon sigma bond. So this kind of an overlap can be seen in case of an sigma bond. And now in case of an this so it is at the axis. Here you can see it is at the axis. Uh, but in case of an bent bond, Overlap, it is not at the axis, or overlap, it is not the lateral. When it is lateral overlap, it becomes pi bond. For that, this two, they should be parallel. These two orbitals, they should be parallel, and then there can be an overlap, and it is said to be an pi bond. But it is not an pi, or it is not an sigma. When it is sigma, it is at the axis, and when it is pi, it is at the lateral side, or side overlap. For that side, it should be parallel to each other. But band bond, and due to this overlap, band bond, it forms a poor overlap, and it is not a stronger overlap, and that is why the structure of cyclopropane, the carbon-carbon bond, it becomes weaker. When it is straight line, so when it is straight line, it will be quite strong. But due to this side, as per the theory, due to this type of an overlap, it makes the carbon-carbon bond weaker. So according to the bear strain theory, the configuration of an cyclopropane is a triangle with a carbon angle of an 60 degree. So Coulson and Moffat's propose that smallest carbon angle which can be reasonably expected to have 104 degree. So this theory tries to explain the carbon bond angle. It is not a 60 degree, but it is 104 degree, so it is closer to the tetrahedral. So what it has been expected that we should have a tetrahedral geometry when it is sp3 hybridized and having a 109 degree angle. So this theory, or this model, it is explaining how it can be 104 and how it cannot be an 60 degree. Therefore suggested that cyclopropane only partially overlap of sp3 hybrid orbital occurs. So the carbon-carbon-carbon bond angle is decreased slightly from 109.5 degree to 104 degree, and this carbon hydrogen angle increased to 120 degree compared to the normal tetrahedral angle. So what this theory is trying to explaining that carbon angle. So all the carbon, when it is tetrahedral structure, all the angle it should be 109.5 degree, but it is not, and it is 104 between carbon carbon, and once it is for an carbon hydrogen. So as per this theory, Coulson and Moffat's model, so this angle has been increased to 120 degree. So somewhere it has been compensated. At carbon-carbon it has been compressed, but it has widened for an carbon-hydrogen. So slightly from the normal it has been increased for carbon-hydrogen and decreased in case of an carbon-carbon bond. So here you can see the structure of an cyclopropane. See this structure, it is indicating whenever there is an overlap of this sp3 hybrid orbitals, a pp orbital we can say of an carbon. So this overlap, it should be at this line to form an covalent bond, but it is not, and it is forming a band bond. So the electron density, so from this line, electron density has been shifted. So electron density has been shifted, and due to which electron distribution has been changed. Once it is on the line, then electrons are distributed on both the sides similar, and that is why it forms covalent stronger bond. And these hydrogens, they are indicating above and below the plane. So this broad line, they are indicating above the plane, and dotted line, they are indicating below the plane of an carbon of hydrogens. Prefix cyclo is used to name the corresponding normal alkane having the same number of a carbon atom in the ring, and the substituent on the ring are named according to their position indicated by the number. So in case when it is only one substituent, so there is no need to number the ring. If it is only one substituent with no modifications, it should be an alkane, so it will be different for an alkene. So it will depend on a double bond where the location of that double bond it is, and the substituent. So also we have seen one example having two substituents. So there should be a minimum numbering between the carbons, and the priority should be given to a substituent which has an highest priority. So we have seen the chloro and methyl group in case of that nomenclature. After that, certain symbols they are being utilized for convenience or to draw the structure in case of reactions. So instead of writing that CH2 in each corner, for convenience and simplicity, cycloalkanes are often used represented by simple geometric figures, and each corner represent one carbon and two hydrogens. So by simply making square, by making triangle, and by making pentagon or by making hexagon, so these structures can be written very easily, and it will also help for the students for writing the reactions. And by writing such kind of symbols, so it becomes easy that student will not miss the number of hydrogens, placing number of hydrogen on a carbon. So carbon it will be, but some student they miss hydrogens when writing of a reaction, so it becomes inconvenient to write also the reactions. So these are some geometric simple figures that are being utilized by a chemist for cycloalkanes. So we have seen the Baer strain theory. So Baer postulated that any deviation of an bond angle from a normal tetrahedral value will impose a condition of an internal strain in the ring, and as the strain, so we will see one by one example. The angle strain in cycloalkanes, so first compound, after that bond angle, and after that angle strain. So cyclopropene, so bond angle it is 60 degree and angle strain it is 24 degree and 44 minutes. After that, cyclobutanes. So cyclobutane has bond angle 90 degree as it is represented by n square, and angle strain it is 9 degree and 44 minute. After that, cyclopentane. So cyclopentane has bond angle 108 degree and angle strain 0 degree and 44 minutes. After that, cyclohexane. So cyclohexane has bond angle 120 degree and angle strain it is minus 5 degree and 16 minutes. So from this Baer strain theory, so Baer strain theory is applicable to only some fewer cycloalkanes like cyclopropene, cyclobutane and cyclopentane. So it has explained only reactivity up to this. So it has not explained the reactivity further for an cyclohexane, because in case of an cyclohexane and cyclohexane derivatives and higher cyclohexane or more higher compounds than an cyclohexane, they show the stability, and this stability is more than the cyclopentane in case of an cyclohexane also, though as per the Baer strain theory it has been explained that it is having a negative angle strain, that it has widened the structure of an carbon. So it should be 109 degree for a normal tetrahedral, but it has increased to 120 degree in case of an cyclohexane. So this theory has failed to explain about an cyclohexane. So as the angle strain increases, so as the angle strain has been increased, so instability of the compound has also increased. So means cyclopropene it is more unstable then cyclobutane, then cyclopentane, and also cyclohexane. Uh, so it depends on what kind of a structure it is having. So cyclopropane, it is equilateral triangle and having a 60 degree. So it is quite compressed, and due to this compression, the angle strain, it is having quite higher angle strain. So cyclopropane is the first molecule, or it is the first member from this cycloalkane family, and the stability, due to its instability of an cyclopropane, it undergoes the ring opening reactions very easily. But compared to that cyclobutane, ring opening reactions are not so easy. It requires drastic conditions, and in case of an cyclohexane, so there are no ring opening type of reactions, though it is having a negative angle strain. So as per the Bayer's theory, so negative angle strain should increase for an cyclohexane and higher derivatives than cyclohexane, and as the negative angle strain also increases, instability also increases. But it does not happen in the actual, because it is having some different structures at the normal condition. So we will be looking in another theory in the after that. We have seen the modification of an Bayer strain theory, that is Coulson-Moffat's modification, or also it is said to be a banana theory, or also it is said to be in bend bond theory. So bend bond theory, or bend bond, it is a bond between carbon-carbon, sigma bond, and carbon-carbon pi bond. So that overlap, it is not either lateral or it is not an axial. So it is in between overlap. So electron density or configuration of a molecule changes, and due to the electron density, it has been shifted, or the configuration do changes. The bond, carbon-carbon bond, becomes weaker. So theory is based on the bend bond formation by overlap of an sp3 hybrid orbital between carbon-carbon bond of an cycloalkanes, which makes weaker bond between carbon-carbon, pointing electron density or configuration outward, and relieving strain between carbon-carbon. So relieving strain between carbon-carbon means what? That Bayer strain theory, it has explained that the carbon-carbon bond between the cyclopropane, it is compressed up to an 60 degree. But as per this modification, so as per this model, so this angle between carbon-carbon, it is 104, and that angle, it looks like banana, and due to which carbon-carbon bond becomes weaker, and it is easily susceptible for opening of a ring and undergo the opening ring opening.